Far from cities, roads, and ordinary routines, there is a place where the air feels older than memory. Antarctica is quiet in a way that is difficult to describe. Not the quiet of silence, but the quiet of distance. Sound does not travel far. Human presence barely leaves a trace. For most of the year, the continent rests under cold light, pale skies, and long shadows that move slowly across ice. In the middle of this landscape, small research stations have existed for decades. They were never meant to be dramatic places. They were built to endure. Inside them, scientists performed work that was repetitive, careful, and often lonely. Measurements were taken at the same times each day. Instruments were checked and recalibrated. Numbers were written down, reviewed, and compared with earlier numbers. Most days looked like the days before. Among the things being measured was ozone. Ozone is a form of oxygen that exists high in the atmosphere. It is not something people can see or touch directly. It forms a thin layer spread around the planet, absorbing much of the sun's ultraviolet radiation before it reaches the surface. Without this layer, sunlight would damage living tissue more easily. Skin cancers would increase, crops would suffer, ocean ecosystems would weaken. The ozone layer is not thick, not solid, and not uniform. It is fragile, invisible, and essential. By the middle of the 20th century, scientists already understood that certain industrial chemicals could affect atmospheric chemistry. But understanding in theory is different from observation. To truly know what is happening, you must measure it consistently in the same place, using the same methods over long periods of time. That was the work being done in Antarctica. Each day, instruments measured how much ozone was present in the atmosphere above the station. One of the tools used was a simple optical device that measured how sunlight was absorbed at different wavelengths. The readings were recorded by hand. They were unremarkable most of the time. Numbers rose and fell slightly with the seasons, as expected. The data fit established patterns. Then, gradually, something changed. The change did not arrive as an alarm. There were no sudden failures or dramatic moments. The numbers were simply lower than expected. At first, the readings seemed wrong. Instruments in extreme environments are prone to error. Cold can affect electronics. Frost can interfere with optics. Human error is always possible. So the scientists did what they always did when something looked unusual. They checked the instruments. They recalibrated. They repeated measurements. They compared notes. The numbers stayed low. What made this unsettling was not a single day's result, but the pattern. Over time, the springtime ozone levels above Antarctica were dropping far below historical averages. Not slightly, not gradually, dramatically. Still, caution ruled the response. Extraordinary claims require extraordinary confidence. The scientists did not rush to conclusions. They examined older data. They confirmed that the decline was not an artifact of changing methods. They looked for explanations that did not involve a real atmospheric change. At the same time, satellite instruments orbiting Earth were collecting their own ozone data. Satellites provided global coverage, but they relied on complex processing and assumptions. In some early analyses, satellite systems had been programmed to discard extremely low ozone readings, assuming they were errors. In effect, the most alarming data points were filtered out automatically. Ground-based measurements in Antarctica did not have that filter. When scientists compared the two sources carefully, a clearer picture emerged. Over Antarctica, during the southern hemisphere spring, a massive region of severely depleted ozone was forming each year. It was not a hole in the literal sense. Nothing had been punched through the atmosphere. But, relative to surrounding areas, ozone concentrations were so low that hole became a useful shorthand. The discovery was unsettling precisely because it was quiet. There was no explosion, no visible damage. The ice looked the same. The sky looked the same. People living far away felt nothing different in their daily lives. Yet, high above the surface, the chemistry of the atmosphere had shifted in a way that mattered to everyone. The cause was not a mystery for long. Certain man-made chemicals, particularly chlorofluorocarbons, had been widely used for decades. They were valued because they were stable, non-toxic, and effective as refrigerants and aerosol propellants. Their stability, however, meant that once released, they persisted in the atmosphere for many years. Eventually, they drifted upward into the stratosphere. There, under ultraviolet light, they broke apart and released chlorine atoms. A single chlorine atom can destroy thousands of ozone molecules through catalytic reactions. The process is slow, invisible, and relentless. Antarctica turned out to be a perfect place for this chemistry to concentrate. The extreme cold created polar stratospheric clouds, which enabled reactions that converted chlorine into its most destructive forms. When sunlight returned after the long polar winter, ozone destruction accelerated rapidly. The measurements from Antarctica were not predicting a future problem. They were describing a present reality. When the findings were shared with the broader scientific community, they were met with scrutiny, as they should have been. Independent teams analyzed data from other sources. Atmospheric models were refined. Laboratory chemistry experiments confirmed the mechanisms involved. Gradually, consensus formed. The ozone hole was real. What followed was not instant action, but steady, coordinated response. Governments, industries, and scientists worked through international frameworks. Alternatives to harmful chemicals were identified and developed. Regulations were negotiated and adopted. Timelines were set, extended, revised, and enforced. The process was slow by design. It required trust in data, patience with uncertainty, and willingness to act before visible catastrophe forced the issue. Throughout it all, the measurements continued. Year after year, scientists returned to Antarctica. Instruments were upgraded, but continuity was preserved. The same questions were asked in the same way. How much ozone is there today? How does it compare to last year, to 10 years ago? Over time, the data began to show something else. The decline slowed, then it stabilized. In some years, modest improvements appeared. The ozone hole still formed each spring, but its growth no longer followed the earlier trajectory. Recovery, scientists explained, would take decades. The chemicals involved persist for a long time. Atmospheric circulation is slow. Patience remains necessary. Even now, the most important work is still quiet work. There is no daily headline announcing incremental improvement. The success of ozone protection is measured in continued absence of disaster. Skin cancer rates that do not rise as fast as they might have. Crops that grow as expected. Ecosystems that remain stable. Most people will never think about ozone while falling asleep at night. They do not need to. That is the point. The day the ozone hole was measured was not a single dramatic moment. It was the accumulation of ordinary days, of careful notes, of instruments checked in cold rooms, of scientists who trusted numbers enough to question them, and questioned them enough to trust them again. Nothing exploded, nothing collapsed. The ice remained still, the sky remained blue. And because of that quiet work, it still does.